Okay, so I gave you a few problems to work on. Anybody have any questions about those? I'd be happy to. I know there were at least a couple of them that there weren't solutions for. Uh, want me to go over any of those? Yep.
Professor, for number two, like when the problem says like he added versus work done,
Yeah.
like is there a distinction between being added to the system and work being done to the system?
Okay, so
And is that like the difference? So if
yeah,
work is done on the system, then that's like a negative W
if that's right. That's right. So
versus if it's
work is either done on the system or on the surroundings by the system. If it's done on the surroundings by the system, then that the W is positive. If it's done on the system, then W is negative. Let me just, I'd be happy to do both of these, but let me at least do one. Um, let's just go through number two. Okay. So, okay, so here's number two. Um, so it says, 20 times 10 to the sixth joules of energy is lost from a gas through heat. The system is the gas. That's what we're focusing on. Think of that as like the thermodynamics version of like your free body diagram or whatever. That's the thing you're analyzing. And um, 15 times 10 to the 6 joules of energy is done to the gas through work. Okay, well, Q is positive when it's added to the gas. Because the gas is our system. That's what we're focusing on. Okay. W is positive when done by the gas. That's the sign convention here. So if 20 times 10 to the 6 joules of energy is lost from the gas, subtracted from the gas, this Q is going to be, you can think of it as like, okay, we already know they give us this number 20 times 10 to the 6. We just have to think about whether it's positive or negative. And in this case, it's removed from the gas, so we want the negative. Then for work, that's plus or minus 15 times 10 to the 6 joules. It says that this is work that's done on the gas. W is positive if it's done by the gas on the surroundings, so this is also negative. So now you can, so these are the answers to, this is A is negative 20 times 10 to the 6. You don't have to carry units through your calculations, but always put units on your answers. Okay. So this is negative 15 times 10 to the 6 for part B. For part C, what's the change in energy? Well, the first law says the change in energy of the system, the gas in this case, is equal to Q minus W. So that is negative 20 times 10 to the 6 minus negative 15 times 10 to the 6. And so that's negative 5 times 10 to the 6 joules. Okay? And then the last question is, do these values that we calculated, Q, W, delta E, represent property values at a single state, or do they represent a process? This is saying that from some instant 1 to some instant 2, this much heat is added, this much work is added. And let's see. This is the change in energy from instant 1 to instant 2. So these represent what's happening during a process. And anytime we use the first law, or the second law, actually, but that won't come up for a while, we'll be representing a process. So the first law always represents a process. Any questions about that thought process? Okay. So today we're going to get into pressure and temperature. So I'm going to start by defining pressure. We're mainly going to, you can have pressure that's applied to, well, often you'll have fluids applying pressures to solid objects. You don't usually talk about the pressure inside a solid object, but, mainly we're going to talk about these in fluids. And by fluids, I'm talking about liquids and gases. We're going to see, by the way, in this class, almost everything that we're going to be talking about is going to be liquids and gases. And there is a very simple reason for that. We're talking about engineering processes for the most part. We're talking about ways that we can use thermal energy to cause mechanical energy or vice versa. And how many of you had a brief section on thermodynamics in your Physics 1 class? Anybody? A couple people? Yeah. So you might have talked about latent heat, the heat that's required to transition from one phase to another phase. There's a small amount of energy that is there's a small amount of energy that's stored in a liquid that you can release by turning it into a solid. Not very much. Okay, but there's a huge amount of energy that's stored in a gas that you can release by turning it into a liquid. Okay, and there's a reason that latent heat is an important thing. You can access that latent heat without changing the temperature of the material at all. Like water that's just about to turn to ice has the same temperature as ice that's just about to turn to water. So anyways, the basic, all I'm trying to say is in going from a liquid to a gas, there's a ton of energy that's available there, that you can use to turn it into a gas. Once it's a gas, You can extract that to turn it into a liquid without changing the temperature of the material. And that's a very useful thing for engineers. There's a ton of energy that you can extract without worrying about changing the temperature. And so we'll talk about that later. But that's the reason that gases and liquids are important to us. The transition from liquids to solids, we don't really care about that much, okay, as engineers. So pressure is the force per area that's applied by a fluid perpendicularly to any surface. The units are always units of force divided by units of length squared for area. And so the SI units for pressure are newtons per meter squared, and that is the name pascals. So the SI units for pressure is pascals. So here is sort of how it works, relating pressure to forces and stuff like that. So if you have, let's say you have this pressure vessel, and inside there's this object, and then this is all filled with a fluid. Let's say it's a gas. Okay. What's the direction of the force that this pressure in this gas is applying to the outer walls and then to this object inside? Okay. So what's the force direction that the gas pressure applies to first, let's say the vessel walls, and then second to the object inside. Yep.
When you said vessel wall, do you mean the circle thing?
Yeah. So let's say that's like a container. So vessel is just as, not, I don't mean blood vessel necessarily, but just the container. Okay, so free body diagram of the vessel. So there are the walls. Pressure always applies a force perpendicularly to what it's contacting, and it's always toward the object that it's contacting. So the force vectors are going to be like this the whole way along, perpendicular at every location. Okay. And then what about so this is for part A. For part B, if we draw a free body diagram of the object, it's going to be perpendicular to this. Pressure can only apply forces toward the object, so those are the directions of the forces. If a fluid, so a gas or a liquid, is continuous, so the fluid can flow from one place to the other without being stopped by walls or something. And at rest, then you can find a relationship between pressures at two different heights. So this is a relationship between pressures at different heights. And the relationship is the pressure at the lower height is equal to the pressure at the greater height plus the density of the fluid times the acceleration of gravity times the difference in heights between those two. So this is the density of the fluid. This G is, as long as we're on the surface of the earth, 9.8 meters per second squared. And H is the difference in heights between those 2 points of interest. Yep.
Professor, what is like bar? That's like another pressure thing, right?
Oh, yeah. One bar is 1 times 10 to the 5th pascals. And that's sort of in the ballpark of our standard atmospheric pressure. Standard atmospheric pressure is 1.01 times 10 to the 5th. So just for using like nice size numbers, bar is a nice unit for thinking about pressure. So, yeah.
Can you explain to me what is pressure low and pressure high again?
Yes, we're talking about so if you have so let's say that we have 2 points underwater, okay, and we want to know the pressure here and here, or the difference in pressures between those two. So this is just the low.
Okay.
This is the high.
So the low is how low it is.
Yeah, the height.
Oh,
So which one is lower, has a smaller height, And so the difference between those, another way you could think of it is, the change in pressures, which is P low minus P high, is rho G H. So if you know the density of the water, which is about 1 times 10 to the third, almost exactly 1 times 10 to the third kilograms per cubic meter, then you can calculate that. This is actually, sometimes it's nice to have quick little derivations in your head so you can remember that stuff makes sense. So if you ever want to derive that expression, think of the weight of the fluid between the high point and the low point. Okay, so like for example, let's think of a square cross section, and then this is all fluid. This is the high point, and this is the low point. Okay, the pressure, the difference in pressure between these two is created by the weight of this column of fluid. Okay, this is fluid. Okay, so let's think about what the weight of, can you picture what I'm getting at here? Like we're gonna treat this as our baseline for pressure, the top. We'll just call that zero pressure. What we're gonna figure out is the difference in these pressures. And we wanna figure out the pressure that's applied to like this square plate at the lower height. Okay. Well, so the force on the lower height is mg, and the density is the mass per volume, and we know that this is what we're calling h, by the way. And so we can break the mass up into the volume times the density, and then we have to multiply that g on. And now we can break that volume up into the area of the square, that cross section, times the height. So this is area times height times rho times g. Okay. So this is the total weight. Come back. But the definition of pressure is a force per area. So that's A, H, rho, G, divided by area. The areas cancel, and you get what we had before. Rearrange it again, but so that's the difference in pressure. Okay. So why doesn't this formula work for two cases. Okay, so first, let's think about an inner tube for a tire. So here's the tube. Okay. Inside the tube, after you pump it up, you have a really big pressure compared to out here, say at the same height of this inner tube, you have a small pressure. So what's the deal there? The height doesn't tell us the difference in pressure. Why doesn't it work?
Because it's not open.
Yeah, because it's not continuous. Another thing that we're going to see a lot is what about fluid that's traveling through a pipe like this? So if fluid is going this direction, over here, it has a high pressure as it has a low velocity. Here it has a low pressure as the velocity gets higher, and here it has a high pressure again. So why doesn't the equation work in this case? Not at rest, exactly. So this is something like to always ask yourself in any engineering science class or whatever, when you see an equation, remind yourself that the key to using it is understanding what the restrictions are. Okay, what are the restrictions here? This works for any fluid, but the fluid has to be continuous and at rest. Okay. Okay, let's think of an example with pressure. So let's imagine a box that's sealed at sea level. Oh, before I do this, sorry. Put this on hold for a second. So one important distinction with when you're talking about pressure you have to, before you can use any pressure value, you have to know, are you being given an absolute pressure or a gauge pressure? In this class, the pressures we're always going to want are absolute pressures. But there are a lot of cases where the pressure that you're given is a gauge pressure. And the relationship is that the absolute pressure is the gauge pressure plus the atmospheric pressure. If you're using like a tire pressure gauge, that's an example where the pressure that you're reading is not an absolute pressure. It's a gauge pressure that's just basically telling you how much higher the pressure is than the atmospheric pressure. If your tire gets down, like if you slash inner tube and the pressure goes all the way down to zero, or like it totally becomes equilibrated with the atmosphere, um, your your pressure gauge is going to read zero. There's not really a pressure of zero in that tire at that point. It's just saying that the pressure is atmospheric pressure, which is actually still shockingly high. Atmospheric pressure is a lot of pressure. Okay, so let me just give you the standard atmospheric pressure is about 1.01 times 10 to the fifth pascals. Uh, that can vary, but this is what we call standard atmospheric pressure.
That's the pressure at sea level? Or
Yeah.
like 1,000 feet above sea level or something, 600 in that area? So it's only slightly different than that? I don't know.
Yeah. Right. Yeah, it's in that same ballpark, and it fluctuates day to day at sea level and here and everything, but this is what we call standard. Yeah.
Is that also like at a specific like temperature or something?
Yeah. Right.
What temperature?
Well, this it varies with temperature. This is kind of like the value that our barometric pressure sort of oscillates around. You can have this pressure at any temperature, but as the temperature changes, the pressure tends to change too. Okay, so now let's do an example. And so let's say that a box is sealed at sea level. We'll assume that it's standard atmospheric pressure when this box is sealed. And then it's moved to let's say an evacuated chamber where the external pressure is zero. And so just to make the calculations easy, let's say this box has side lengths of 1 meter. So 1 meter cubic container. And we want to figure out what's the net force of the pressure on the shaded wall. So here's the wall we're going to do this for. What creates air pressure? Anyone know, just kind of anecdotally? Yeah. Yeah, so it's just air molecules are just bouncing around off of each other, and this bouncing around makes them want to expand. And so when they try to expand against the walls, they bang against the walls. And it's those collisions that are causing this pressure. And so if you want to evacuate a chamber, what you have to do is get all the air molecules out, and then the pressure is zero. There's nothing to bounce against the walls. And that can be done pretty easily. So, okay, let's calculate the, so here is a free body diagram of that shaded wall. The pressure on the inside of this box is 1.01 times 10 to the fifth. And so the force is 1.01 times 10 to the fifth times the area, which is 1 meter squared. The pressure coming from the outside applied to this wall is zero because there's no pressure. And so there's a force in this direction of 1.01 times 10 to the fifth newtons. Okay, so how much is that? 101,000 newtons. And so just because of the pressure of the atmosphere, there's a force of over 100,000 newtons on this. Think of like your weight in newtons. Say you weigh 80 kilograms. The acceleration of gravity is about 10. So your weight, your entire body weight is 800 newtons. This is over 100,000 newtons. And so most likely, depends what this box is made out of, but for most materials, this is just going to blow that box completely apart. And the force that's going to do that is just entirely standard atmospheric pressure. Okay. This effect is the reason why when you're on an airplane and they bring you a bag of chips, it looks like it's been inflated. Have you ever noticed that? It's because the pressurized cabin of an airplane, they don't pressurize it all the way to standard atmospheric pressure. So it's a little bit lower atmospheric pressure than what it was where the bag was sealed. And so you have atmospheric pressure pushing out on the bag, slightly lower pressure pushing in on the bag. And so it's just this battle between the outward push and the inward push, and the inward push, the outward push of the stuff inside the bag is sort of winning that. Okay. There are two ways to measure pressure. After 40 minutes, my pen needs to get reset for some reason. Okay.
Is that computer kind of like an iPad? Or
It's a yeah. I mean, it's a PC, but yeah. Okay, so there's two main ways to measure pressure. Um, the first one is called a manometer. Um, and it measures the pressure in an enclosed fluid. Um, so it looks something like this. Here's the side that contains the fluid you're trying to measure. I guess really this, in most cases, would have to be a gas. So this is the fluid pressure P that you're trying to measure. And you have a liquid through this part of the connected tube. This end is open to the environment. So this is atmospheric pressure. And the difference between the two heights of the ends of the enclosed liquid is H. Okay, so the measurement that you're taking is just seeing what the difference in height there is. And so the pressure in that enclosed fluid is atmospheric pressure plus the density of the liquid, not the density of the fluid, times the acceleration of gravity times that H. And that's just a direct application of the equation that I gave you before for the pressure difference between two heights in a enclosed fluid.
Professor,
Yep.
will we use MMHG for the that one? I saw that was a unit too.
Oh, that is a unit you can use. We won't use it in this class. There might be a problem or two where that I got out of a book that makes you do a conversion or whatever. But I'd say just always convert to SI units. You can just Google the conversion. You don't even, all that stuff you had to learn about converting units and stuff, like you can forget about that and just Google. Okay, so this is a way to measure the pressure in this enclosed fluid that would usually be a gas. Okay. Whatever it is, it can't mix with the liquid here. They have to stay separate. So you could do it with a liquid and an oil or something, with like water and oil or something. And then the second way is a barometer. And this measures atmospheric pressure. And the way this one is configured is you have a column like that. Ooh. Sitting in a dish. And you have a liquid in the dish. So this is a liquid. And the atmospheric pressure is pushing down like this. Up here, the only pressure in this enclosed part is the vapor pressure of the liquid. That's just the pressure of the liquid that's boiling off of this, and they'll use a liquid where this vapor pressure at that temperature is zero, basically zero. And so if we assume that the pressure at the top is zero and the lower pressure is atmospheric pressure, then again, you can use that pressure equation to get you that the atmospheric pressure is equal to zero plus the density of the liquid times acceleration of gravity times h. Okay, let's do one example problem with a barometer. So let's say that here's our setup. And I didn't draw what h is, but maybe you can imagine it would be the difference in the two heights of the liquid. Okay, so let's say that we're at some altitude and we want to measure the barometric pressure. So we take this barometer and what we see is, and we have to know what that liquid is. So let's say that as our liquid, we use mercury. And we need to know the density of mercury in order to do this calculation. It is 13,690 kilograms per cubic meter. The density of water is 1,000 kilograms per cubic meter. The density of steel is about 7,000 kilograms per cubic meter. So mercury is about twice as dense as steel. A cubic meter of mercury weighs about twice as much as a cubic meter of steel. And let's say that the measurement we get, once we set this up, we see a difference in heights here of 0.55 meters. And we want to know what's the atmospheric pressure there. Well, the equation says that the atmospheric pressure is the density of mercury times the acceleration of gravity, I said 9.8 before. In this calculation, I'm using 9.81. It's about 9.806. So either one of those is kind of okay. Times a height difference of 0.55. Multiply that all out, and you get 73,800 64 pascals. What was standard atmospheric pressure again?
101.
Yeah, 101. So this is about 3/4, just under 3/4 of standard atmospheric pressure. So you'd expect this is a pretty high altitude. I think at the top of Mount Everest, the air pressure is about half of what it is at sea level. So maybe this is somewhere, about the midpoint. That's a pretty high altitude, maybe 15,000 feet or something of altitude. Any questions about that? Okay, well, I have some pressure related problems I can give you, and I guess it'll be Wednesday then when we'll talk about temperature calculations. And then after we do that, we'll be able to get into some kind of actual thermodynamics. Right now, we're still just sort of setting it up. But yeah, no school on Monday. It is Labor Day. So, okay, have a good long weekend.